So in our last video in the series, we're going to take a look at time dilation. This is the phenomenon where clocks move slower as you get closer to the speed of light. So we're going to have to keep track of two clocks. We're going to have to keep track of our clock. We're going to call that the rest clock. It's going to sit in the lower left-hand corner here. And then we're assigning a clock to our relativistic sphere. And we're actually going to have this clock give us a couple of pieces of information. We're going to have it tell us the time that's on this clock and the speed that this relativistic sphere is traveling at. So we're getting the his time and the magnitude of his velocity. The way we're calculating his time is we're giving him a different time step than we have for us in the rest frame. So for us in the rest frame, we've got a time step of 0.01. That's the time step we've been using. But he's going to get a time step of dt divided by this gamma factor. You remember this gamma factor from last time. This is the thing that determined how squished the scenery became. It's also the factor that determines how delayed his clock becomes. So we're going to have our clock keeping track of the proper time here, and we're going to have his clock keeping track of his local time here. Let's hit Control-2 to run this and see what we get. So we see here he's traveling at 40% of the speed of light, and you can already see a bit of a difference cropping up between our times. So we've got a time of 30 seconds now. He's got a time of 30 now. So he was delayed a couple of seconds there in simulation time. And of course, that's going to become more pronounced the farther along we go. So for example, when we reach 70, he's just now at 64. So the difference in the time becomes more pronounced the farther along the trajectory you go. It also becomes more pronounced the faster he travels. So let's double his momentum. Let's give him a momentum of 1 here. That's not quite going to double the speed because of the relativity factor, but yeah, it gets the speed up to about 0.7 c. So that's about, it's close to doubled. And let's see, we reach 25 seconds and then he reaches 25 seconds now. So you see the delay is increasing as he gets closer to the speed of light. Of course, the thing should reset if we're in the same reference frame that he is. So if I make his momentum 0, then there's no difference in the time. His speed is now 0 c. So now we've got the same time passing by on both of them. Now this is just with constant velocity. We can make this a little bit more interesting by putting in a spring force. So let's put in a spring stiffness here of, let's say, 0.1. And what is his initial position? Okay, so his initial position is in the y direction, so he'll be oscillating up and down now. And you'll be able to see his time move a little bit differently depending on what his speed is. I guess the speed isn't changing all that much. Let's increase that spring stiffness to give him a higher maximum speed. Let's see, we're only getting up to about 0.6 there. Let's up that to a 1. Let's also give him a little bit higher position amplitude here. And basically what you'll be able to see is that as he gets close to the speed of light, his time passage changes. So you see as he gets up to 0.9 c, his time is moving slower. When he gets back to rest at each end, his time is going to move faster. It's going to catch up better with ours. And of course, it's never going to actually catch up with ours. He is forever going to be behind in time, but the rate at which his clock is moving is changing, which is pretty cool. All right, so I'd like to finish out with something cool here. Let's make a second relativistic sphere. Let's give it the color, let's make this one blue. And let's have him move over compared to the other. Let's move him over 2 units. There we go. Let's see. He's also, he's going to need a different name, isn't he? He's also going to have a clock. And we're going to give him, let's give him a different amplitude that he moves with. Actually, ooh, I have a, yeah. Let's have him go up with, let's double his amplitude. There we go. And let's decrease the spring stiffness a little bit. What I want to see is I want to see a difference arise in their clocks. So let's see, we've got a spring stiffness here. And let's actually change this spring stiffness to just go along the spring force to just go along the y direction. So they've each got their spring anchored just directly down below them. Now I have to get this thing to move. So let's copy and paste this portion. Let's separate them so I can keep things straight. And we'll just change all the rel 1s to rel 2 here. rel 2. And basically, we're going to have these things moving in parallel to each other. But we're going to see how their behavior changes, and we're also going to see how their clock time is different based on the different amplitude that we've given them at the beginning. Rel 2, rel 2. And now, of course, I need to have this guy's clock update as well. So let's take this velocity calculation, copy and paste. So I'll have a velocity 2. Relativistic 2, relativistic 2, relativistic 2. I think I've changed all those up here. Yep. And then I need to give him a gamma and give him a different clock. Let's see here. So I need to give him a gamma 2. This velocity 1 needs to be velocity 2. So now he's got a different time step than us and rel 1. So I'll have a gamma 2 down here. Rel 2, rel 2, rel 2. Let's see, and then I just need this to be rel 2 time and velocity 2. All right, I think I've changed all of those. So we'll have a red one and a blue one moving differently. And I'll add a scalar and a vector. Oh, that's right, that's right. Let's see then. Oh yeah, I just need to say times vector 0, 1, 0 to put it in the y direction. There we go. Oh, whoops, I have to give him a different force, don't I? Oops. Let's call that one force 1, and this one force 1. All right, let's try that again. Control 2. There we go. So now we can see this one's going to travel farther. And you notice they're going to have a little bit different period because this one's getting up to a higher speed. He's actually getting very close to getting to a rounded 1.0 c. And you notice that they've got very different times. So both of them have a different time than the rest clock, but they definitely also have different times than each other. In fact, this one is slightly half of this one, which is pretty cool. So anyway, this is a neat topic to me. I hope this is useful to you if you're learning relativity or teaching relativity. This is a neat way to kind of demonstrate it in a way that you obviously can't do this in a lab, but as a computer simulation is a cool way to explore this. So thank you so much for watching. I will see you next time. Bye-bye.